Hello, this is Concrete Path and the lecture third for your RCC. That's those analysis and design of singly reinforced beams. Analysis and design of singly reinforced beam. Singly reinforced beam. So singly reinforced beam means you have this beam. We are placing those reinforcements only in the tension side. In the tension zone, we are using those what you call as steel bars. If I place the steel bars also in the compression zone, that means this is a doubly reinforced beam, But we are not going for that. First case is that we are going for just that what you call as place a reinforcement place it only on the bottom side, that's in the tension zone. In the tension zone for the moment that is sagging bending moment, M sagging. Okay, let's say the dimensions of the beam are, this is width of the beam as B cross section, and there's overall depth. Let's try that capital D as overall depth. Capital D is the overall depth, capital D from top to the bottom. Okay. After that, we would say there's small d that we call as effective depth. We had effective depth up to the center to center distance to the bars, center to center distance to the bars. So up to this point, from the top, I would say this is your effective depth. And there's some effective cover also, that this is EC, effective cover. And finally, we would say if I have the strain diagram from this, I would take that strain diagram in this fashion. Let's go for that. So we are taking the strain at the level of steel. At the level of steel, we are taking that strain value. This is our strain variation. And one more thing is that stress block. The stress block we have in this fashion. Here we have some tensile force D, and from the top it's rectangular up to some point. After that there is parabolic variation. Up to the neutral axis. So this is parabolic variation, and we already calculated that those values, if the location of neutral axis was at xu from the top, so we said this is your 3/7 of xu, and this parabolic part is 4/7 of xu, and overall C was acting somewhere here at some x bar equals to 0.42 xu. Okay, and C total compressive force was equals to 0.36 fck B times xu, and tensile force T was equals to 0.87 fyast. Okay, now we have different varieties of problems that would be coming in this SRB. Let's call it as SRB, singly reinforced beam SRB. So different problems are arising here. First case of problem is that we need to get the moment of resistance. MO, or we can write MU. We need to get this moment of resistance of the section. When your beam cross section is provided, that means when B and D is given, you need to get the value of moment of resistance. Second one is that we need to get the area of the steel required in the tension zone. Area of steel in the tension zone required, AST, when the cross section is given. Okay, and we also know what's the moment you are applying on the structure. What's the bending moment you are applying on this structure? This is given, and we need to get the AST here. We need to get the MU in the first case. We need to get the value of AST in the second case. And third case is that design. We need to design the cross section, and that means design means first you need the design cross section. That means you need to get the dimensions B and D, and also you need to get the steel reinforcement, total area of the steel required for in the tension zone for given bending moment, external bending moment that's applied bending moments. So we need to get these values for that third case, that is design perspective. And let's go one by one. Let's take the first one, that's moment of resistance of section when B and D is given. Width of that section and what you call is depth of the beam is given, effective depth. So I would say when we want to find that moment of resistance, it's of the section, that's a resistance towards external bending moments. So that we can say that was equals to C into Z, or we can equate it with the tensile force into Z, lever arm. What was the value of Z? This was the center between those centroid of C force and centroid of T force. So we can write that C force, centroid of C force and centroid of T force. Centroid of C force and centroid of T force. Centroid of T force. That's the, we can say this is the center to center distance. That we call as lever arm, Z, lever arm. So that was equals to, Z was equals to D minus effective depth minus 0.42 XU. And if we substitute here value of C, I would say 0.36 FCK B times XU, and this lever arm Z minus 0.42 XU. And that also we can equate it with that of P TZ, so 0.87 FY AST and D minus 0.42 XU. Now, first thing we had some steps. Let's talk about the first case. So for the first case, we had to get the step-by-step procedure. We have first we calculate actual neutral axis location, actual neutral axis location. For that, we say what should be the value of XU, and that can be calculated from this equation that if I equate that summation fx equals to 0, C equals to T, that compression equals to tension, C equals to T. If I equate C equals to T, I would say 0.36 FCK B times XU is equals to 0.87 FY AST. And from that, we can get the value of XU equals to 0.87 FY AST divided by 0.36 FCK times B. So this is our location, actual location of neutral axis. And now we got the first one. Now we need to compare this with that axial limiting. Second case is that second point of that second step is that you need to get the value of axial limiting, and that we say that is equals to K times D. Axial limiting is equals to K times D, and the value of K is equals to 0.53, 0.48, and 0.46 for 3 grades of steel. This is for M20, that's mild steel, Fe250. This is for Fe415. This is for Fe500 megapascal. So for different grades of steel, we have different values of K. So from that, we need to compare them. Then third step is that compare that XU and XU limiting. Compare XU and XU limiting. Then we say if the XU is equals to XU limiting, that means this is what you call as balanced section or limiting section. And if the value of XU is lesser than XU limiting, then we would say this is under reinforced section. And we should prefer that under reinforced section. So we should try to keep that XU lesser than XU limiting. We should work on this one. If we got this one, if by calculations, first step and second step, if you got that XU was actually lesser than XU limiting, then the moment of resistance would be calculated is equals to, we represent it in this way also, mu, that's ultimate moment capacity. Mu represent whenever there is U, that's ultimate. Okay, it's accounts all those factors 1.5 also. So moment of resistance is equals to mu. We can write that 0.36 FCK B times XU and D minus 0.42 XU. This is the final calculations that moment of resistance. So we know that equation. Here we have the concern. Here is from this equation we have the concern of XU, whether we should keep XU equals to XU limiting, whether we should take XU actual, whether we should take XU greater than XU limiting. This is for that we are discussing these things. So the XU, for value of XU, we have different variations here. So we said that if the value of, let's remove this part. First, once you compare the values XU and XU limiting, if the value of XU is lesser than XU limiting, we would say this is under reinforced section, and we would prefer under reinforced section. And for that, we can write that equation mu equals to 0.36 FCK B times XU d minus 0.42 XU. And the value of XU is here. That is the actual value we have from the calculations. From the first step we have. From that, you have to take that same value here, XU. Now, let's say that somehow that if the case arises that second case, if the XU was equals to XU limiting, that means the section has developed as balanced section or limiting section. Okay, for that case, we will take XU equals to XU limiting. So I would say moment of resistance equals to 0.36 FCK B times XU limiting d minus 0.42 XU limiting. And the third case is that if the value of XU came out to be greater than XU limiting, so our section was developed as over reinforced section, ORS, and the code says that we should not prefer ORS. We should not prefer ORS because your steel is not getting utilized properly, steel unutilized, because it's not going under yielding. We want yielding of the steel. For that, strains should be more than that minimum value we have from the code, 0.002 plus 0.87 Fi by ES. So in this case, that particular strain value does not reach. So we have to ensure that. For that, I would say keep the value of XU, go for XU limiting in the calculation. Take the value of X as XU limiting in the calculation, and I would say moment of resistance for the third case is also equals to 0.36 FCK B times XU limiting d minus 0.42 XU limiting. Okay. You can also solve it. You can also solve it by equation of tensile zone, whatever way you want, whatever way you prefer. Let's go for first case that you want to prefer it by what you call as tensile equation. We have T into Z. We have the T into Z also. We can write that equation also here. We can say that's equals to 0.87 Fy AST and T minus 0.42 XU. That's actual XU. Okay. Second one is that if it is limiting, so we can write 0.87 Fy AST D minus 0.42 XU limiting. And similarly for the third case also, XU limiting. Okay. So once we got it, this was the case one. Now we need to get the AST from the moment and cross section. Now second case is that we need to get the value of AST. What should be the area of steel required corresponding to given moment M applied, external moment applied, and we have dimensions of B and D also provided to you. B and D is provided, and we also know what is the bending moment that's applied on the section. So corresponding to that, we should have an equation of what should be the steel required. What should we take the area of the steel? If I write that equation, 0.36 FCK B times XU equals to 0.87 Fy AST, and from this I can get the value of AST limiting. What should be the limiting area of steel required? If I say what should be the AST limiting required, I would say that is equals to 0.36 FCK B times XU limiting and divided by 0.87 Fy. Here we have to keep that value of XU limiting, and from that we can get AST limiting. And for the given moment we have to see whether this moment, let's write this is external moment. ME is, we say this is bending moment, external bending moment. Factored, we would say this is already we have factored it. That's we have multiplied that loading factor of 1.5 for dead load and live load. This is 1.5. So factored external bending moment. we have to see whether your ME is lesser than MU limiting or not. We have to ensure. So so the case is that the thing is that here I would say for under reinforced section we want that under reinforced section. We want under reinforced section, and for that we should say there should be some value of limiting moment, and that limiting moment should be more as compared to the what you call as external bending moment. If this is that means we have to ensure that our limiting condition is even more than the what you call as external bending moment, such that our by doing some configurations change in what you say BD and steel, we can ensure that our section is under reinforced. So we want to get the equation of MU limiting. We want to get the equation of MU limiting first. First, I want that MU limiting equation. MU limiting. If I write that equation MU limiting, if I write that equation MU equals to 0.87 Fy AST and D minus 0.42 XU. Okay. And we also know that we write 0.36 FCK B times XU D minus 0.42 XU. Now, if I want that MU limiting, what should be the limiting moment of resistance? That we can write MU limiting is limiting moment of resistance. Limiting moment of resistance. And for that, I have to substitute here MU as MU limiting. And here, similarly here, I would say AST limiting and XU as XU limiting. Here we have XU as XU limiting, XU as XU limiting. And we already know what should be the value of XU limiting. That is equals to K times D. K times D. So if we substitute that value here, I would say 0.36 FCK B and K times D, and we have D minus 0.42 and we have K times D. Can we write that here? Can we say we can have the equation in terms of KD? And if I simplify it, 0.36 and we have this let's write FCK side, we have this F CK, we have B, and we have D square common. We can if I keep that D outside, so I would get a value here 1 minus 0.42 K. So we got this equation. And if I simplify this part, and we have one more factor, that's K. So we got this part, and I can name it as a value of Q. And finally, I would say Q times FCK BD square. So MU limiting is equals to Q times FCK BD square. So this is your equation for MU limiting. Q times FCK BD square. And we need to get the for different values of for different grades of steel, we already know the value of K, and from that I can get the value of Q for different grades of steel, and we have calculated those values. If we have mild steel, if you talk about mild steel, we already write somewhere we already have written those values. Yeah, we can write here. We can write that value here, value of Q. This was the value of K, and we can write value of Q also. So once you substitute the values of K in that that's constant part of that equation MU limiting, you would get value of Q. This one is equals to 0.148. This is 0.138. This is 0.133. So these three values we have to remember: 148, 138, 133. Okay. So we got the value of Q, and we know that what is the characteristic compressive strength of the what you call as concrete. We already know the dimensions BD square, so we can get the value of MU limiting. Then we compare that MU limiting with that M external. We then compare MU with the MU limiting. This is M external. We want to compare then what is the external bending moment greater or lesser than your limiting moment? Okay. So for that we should prefer that limiting moment is more. Now if this is lesser, if let's say condition arises that if this value was lesser, if that means this is lesser than limiting condition, so I would say AST should be calculated as per one of the equations. So we can derive that equation also. So let's keep it for some time. Let's keep it for some time. We will get the value of, we want to get the equation of AST. We want to get the value of equation of AST. We want to get the equation of AST. So we have this moment of resistance. We have this moment of resistance. Let's try, let's solve it in terms of steel, area of steel. So I would say we have 0.87, we have Fy, we have AST, and we have what you call as D minus 0.42. And if you substitute the value of XU, if you substitute the value of XU as if you substitute the value of XU as this one, this equation, we have 0.87 FyAST, 0.87 FyAST divided by 0.36 FCKB. And then further simplification, on further simplification you would get equation, you remove this limiting, you remove this limiting, you remove this limiting, and you can get the equation that AST equals to, this is the simplified equation we have, 0.5 FCK by Fy and BD into 1 minus root of 1 minus 4.6 bending moment, and we had to keep it in terms of 10 to the power 6. We had to factor that 10 to the power 6 also. If the mu was in kilonewton meter, so then we had to multiply that 10 to the power 6 such that it becomes Newton millimeter, divided by 10 to the power what you call as FCK and BD square. This is our equation for AST required. So you have to keep it as an important one. So this is your equation. AST equals to 0.5 FCK by Fy, FCK by Fy, BD bracket 1 minus root of 1 minus 4.6 mu by FCK BD square. Okay, this is our equation. And if the condition was such that your external bending moment you are applying on the structure that are lesser than limiting condition, that means you can solve AST corresponding to M external. You can solve AST corresponding to M external. Let's try that M external here. So corresponding to this condition at the top, if this is happening, if this happened, so you had to write that AST corresponding to M external. But if the second case is that if M external was equals to MU limiting, so we had to say we had to keep that, we had to solve for AST limiting. We need to get the value of AST as AST limiting. And similarly in the equation we have to, in the root of that equation we have to keep that MU limiting, equation of MU limiting. And if the third case is that ME was greater than MU limiting, still we have to use that AST as AST limiting. Or we have to either revise the section. Either we have to revise the section, maybe we have to revise the section. Let's keep it further as of now. We are going further from this those problems also we can get that. Okay, third case. Now we are going for third case. Third case is saying if we want to design cross section for bending moment. Design cross section for bending moment. There is bending moment applied, M external, ME. Then we have to design. We want. If this was your third case, we want that under reinforced section. We want section to be under reinforced. So for that, our moment, even the limiting condition is that our limiting moment should be greater than M external. This is the condition that even for the what you call as if I talk about balanced section, I would say limiting moment should be equals to external moment. This is balanced section. But if I prefer under reinforced section, I should say this should be greater than. Limiting condition should be greater than. This would ensure that your limiting moments are more than external moments, and that itself will ensure that section is under reinforced. If I say what is the value of MU limiting, the value of MU limiting equals to Q times FCK BD square, and that should be equals to, that should be greater than, not equals to. For under reinforced section, If I want under reinforced section, I should say your limiting moment should be greater than external moment that you are applying on the structure. So from that, I can say I need to get the cross section. That means we need to get the value of B and D, and after that we need to get the steel area. But let's say we are going to assume B. B we can assume. If I assume that value of B, I can get some approximate value of D. I can get the approximate value of D. Or if the B is given, it may be B dimension may be given, or we can assume it. If we assume it, then we can get the value of the depth of section required. So from this we can get the value of depth required. So depth would be greater than ME by Q times FCK times B, and all that under root. Okay, this is the one more important equation we have. That depth should be greater than ME by Q FCK BD squared. This equation, when I write that it should be greater than this condition, this ensures that structure is under reinforced section. Ensures under reinforced section. So this one is your important. This one is your very important. Okay. Okay. Okay, everything is perfect. Okay. Okay. Now, one more condition is that we call as limiting percentage tensile reinforcement. Limiting percentage tensile reinforcement. Limiting percentage tensile reinforcement. Reinforcement. We write it as PT limiting. PT limiting percentage tensile limiting reinforcement. Okay, that we say this is the how much AST we are providing. AST limiting, that means the area of steel. You have this cross section. What is the total area of the steel out of the total cross section area of BD? B, and we have this B and D. We have this B, and we have this effective depth. We are talking in terms of effective depth, not total depth. So this one is that AST limiting divided by BD, and this is in percentage. That PT limiting, this is your PT limiting percentage tensile reinforcement limiting, that's AST limiting divided by B and small d. So keep that as a small d. This is your small d, and into 100. Okay, and in this case we would get PT limiting. Okay, now if I substitute the value of AST from the equation we have, we know the equation of AST. Do we know the equation of AST? From C equals to T, I would say 0.36 FCK B times XU divided by 0.87 FY AST. This is AST. This is the equation of AST. And if I want AST limiting, I would say you have to keep XU as XU limiting. All other parameters you can't change. Only you can change the location of neutral axis and AST limiting. So AST limiting is this equation. We substitute here. I would get PT limiting equals to AST. Let's write that in this fashion: 0.36 FCK B XU limiting divided by 0.87 FY, and you have this. We have this 100 by BD also. 100 by BD, and we can get the equation. When you solve it, you would get a value of PT limiting equals to some factor into FCK by FY, and we have this factor of, see, if we have this B and B gets cancelled, we are left with XU limiting by D. And we know that XU limiting is itself equals to KD. Is it equals to KD? So that means overall value is equals to K. Can you write that? Overall value equals to K. And this part we have the factor we have, that is equals to 41.38. Overall calculation of this one, and this one. Okay, this is equals to 41.38. So finally your PT limiting is 41.38 K times FCK by FY. Okay, This is the limiting condition, that what should be the percentage limiting area of the steel or with respect to the BD area we have. Now, once we solved it, BT limiting, and we compare then once we provide the AST also from the equation we have earlier, we talked about the earlier condition, that AST. Where was the AST we have? AST. Yeah, this was your AST. This was your AST, and from that you can get AST limiting. You can get the value of AST, and if you divide by BD into 100, multiply 100, so that we can get as PT for that given section. Then we compare that PT versus PT limiting. PT versus PT limiting. If PT was greater than PT limiting, that means you have used more steel. More steel has been used. That means it's under over reinforced section. And if the PT was lesser than PT limiting, that means section is under reinforced section. Okay. So final crux is that we had to ensure that in solving the problems you had to ensure that section is under reinforced section. And you should, if somehow we got what you call as under reinforced section, we have to revise the section. Revise the section. That means either we have to change the D we have to change, or we have to change the B, or we have to change the steel area. We have to change those section dimensions and steel area such that it comes back to as a section of under reinforced. We should ensure that under reinforced section. If somehow there is ORS, we should revise that section, change diameter, change depth, change D, change B, AST, accordingly any of that data such that it becomes under reinforced section. And after that, we know that under reinforced section, for the under reinforced section, we should have XU lesser than XU limiting. We should have MU lesser than MU limiting. We should have what I call as third one is that we should have third case is that we should have AST lesser than AST limiting, or we can write PT also. PT also, because we have PT is actually AST divided by BT and 100. And this part this is a constant factor, so we can say PT or AST directly. We can say AST lesser than AST limiting. So these are the criteria for URS. Okay. You can solve either of the three, and you can get whether the section is under reinforced or over reinforced. Let's go for the problems we can take. First one. Let's go for the first one. Let's go for the first problem we have related to the singly reinforced beams. So this is our first problem. We need to get the moment of resistance of section. If the section is provided to you with the dimensions of B, this is 400 B millimeters, and we have effective depth. Total depth we have D 600 millimeter, and we have effective cover. Effective cover is equals to 50 millimeter, and we have different cases of the problem. First case is that we have four number of 25 bars. That means diameter is 20 millimeter, and we have four number of bars of that diameter. So 4 bars we have 1, 2, 3, 4. At some locations such that we have effective cover equals to. So this is AC equals to 50 millimeter. So what should be the value of small d? What is the value of small d? Can you tell me? What is the effective depth we have? Effective depth equals to 600 minus 50. So effective depth is 550 millimeters. So for the first case, we need to get the moment of resistance of the section. So it's easy. So we need first step for calculation of that moment of resistance when the section dimensions are provided to you is that get the location of neutral axis, actual location of neutral axis. So I would say actual location of neutral axis is equals to 0.87 Fy AST by 0.36 FCK times B. And we forgot that material. We have material of Fe415, and we have M20 concrete. That means FCK is M20, that 20 megapascals, and steel is having Fy415. So let's substitute those values. I would say 0.87 Fy AST. What's the AST value we have? Area of the steel. For the first case, that's 4 times pi by 4, 20 square. That's the area of the steel bars in the section. That is this area of the cross section of those bars. And divided by 0.36 FCK, and the width we have B, 400 millimeters. 400 millimeters. So you would get a value of XU equals to 157.53 millimeters. Now, second step is that we have to compare it with that XU limiting. So if the value of XU limiting is equals to K times D, now I substitute the value of K and D for the Fe4 and 5. So we know that for the Fe4 and 5, your K value equals to 0.48, and the value of D is equals to 550 millimeters. This is the effective depth, 550 millimeters. So XL limiting is equals to 264 millimeters. Now, the third step is that comparing these two values. What can you tell me about that 1 and 2, XU and XU limiting? I would say that XU limiting, I would say XU is equals to 157.53, and that is lesser than XU limiting. That means we can say this is under reinforced section. Can we say that? I think we can say that. So that means we can write the moment of resistance as MOR equals to 0.36 FCK. This is FCK. FCK B. The value of B was 300 millimeters. 400. Yeah, B is equals to 400. B equals to 400. B. 400 B, FCK B, then we have XU. What should we use the value of XU? We have the equation of XU. So we have this equation 0.36 FCK B XU. We have to substitute the value of XU as the value of actual XU. That's the section having under reinforced section. So XU equals to 157.53, and we have this lever arm D minus the value of D was 550 minus 0.42 XU. So we can get the final equation, final solution, and the value of all of this is that value is in Newton millimeters. So we have to then we have this factor 10 to the power 6 also here. Then finally, if you divide that, you would get some value. You would get some value equals to 219.52. Such that finally your overall moment of resistance is 219.52 kilonewton meter. So once you got that answer, you have to divide by 10 to the power 6. This is actually in the calculator you would say divide that 10 to the power 6. When you divide that 10 to the power 6 in the calculations, so you would get a final value in this way, such that the units you would say final units are in kilonewton meter. Okay. This is, you have to divide this part. You have to divide it. So finally, you got a moment of resistance for the first case. Now we need that second case is also that we have 8 number of 25 bars, 25 diameter, 8 number of 25 5 bars. The diameter is 25, and we have 8 number of bars. So we can write here we have 8 number of bars, and the diameter is 25 square, and that we can say your equation of XU would be calculated to that finally equals to 492.28 millimeters. And the value of XU limiting is constant. It does not change by changing those bars, number of bars. So that is fixed. So I would say your XU actually is more than XU limiting. So your XU and that XU is greater than XU limiting now. For the second case, that means I would say XU is greater than XU limiting. That means ORS, under an OR reinforced section. So what should we write now equation? What should be our equation then? So we have to keep that. That means we should go with equation that's having XU as XU limiting. So we need to substitute the value of XU as XU limiting. So equation is 0.36 FCK B, and XU limiting we have to use here XU limiting. So we need to remove this part and we need to substitute value of XU limiting 264. We have to substitute here 264, and after that d minus 0.4 to XU, d minus 0.4 to XU, and in terms of XU we have to substitute as XU limiting. That's 264, and you would get a value equals to what we call as 333.87 kilonewton meter. And third part of the problem is that you need to get the moment of resistance of limiting section, and we would say this is also equals to moment of resistance of the limiting section. Can we say that this is the moment of resistance of the limiting section also? Because for the second case we calculated, see, in the second case there is no role of AST. You can see in this equation there is no role of XU, that's steel. Whatever amount of steel you use, your MOR is not going to change. Your MOR limiting is not going to change. See the equation for MOR limiting. For the MOR limiting, we have equation 0.36 FCK B times XU limiting G minus 0.4 to XU limiting. And this part is fixed. XU limiting is a function of grade of steel, and that is also fixed. And everything is fixed. So it does not depend on the AST. So from the part 2, you can also get the part 3. Part 3 of the problem is saying get the moment of resistance, limiting moment of resistance of the section, and accordingly get the area of the steel as limiting area of the steel limiting. Okay, you need to get these two values in the third case of the problem. I would say the equation we have the value of MO, moment of resistance. In the second case we got this one, and that one is also equals to moment of resistance of the limiting section, because by changing the AST, it does not depend on that. Moment of resistance does not depend on that. It depends on the XU limiting, and we have XU limiting. We already got that XU limiting as KD. So your moment of resistance is equals to a moment of resistance limiting, and corresponding to MU limiting, we can get the area of the steel required, that is AST limiting. And we have the equation AST limiting equals to 0.5 FCK by Fy BD. Then we have this bracket of 1 minus root of 1 minus 4.6 MU limiting. We have to use here MU limiting by FCK BD square. Finally, we have this bracket. Close the bracket, and now we substitute the values of those parameters we have. I would say FCK was given to you as 20 megapascals, Fy was 415, B was 400 millimeters. The depth of the cross section, that was 550 millimeters effective depth. 1 is 1, minus is minus, root is root, 1 is 1, minus is minus, 4.6 is already there, and we have to substitute the MU limiting as this value 333.87. So I would write here 333.87 10 to the power 6, 333.87 10 to the power 6, and the value of FCK was 20, value of B was 400, D square is equals to 550 square, and you would get equation AST equals to, you would solve it in the calculator, and you would get AST limiting equals to 2096.84 square millimeters. Okay. One more way we can have by the equation of tensile equation. We have AST from the equation of tensile equation with respect to moment limiting. If I write that MU limiting equals to 0.87 Fy AST limiting, and we have that D minus 0.42 XU, and the value of XU we can write XU limiting and I know the value of XU limiting, and already I also know MU limiting also I know, and I can get the value of AST limiting from this equation also. You can get that by this equation. Let's take the second problem. So we are going to take infinite number of problems, tons of problems on that singly reinforced beams. So different variations of those problems. Second problem is that you need to get the moment of resistance of the section with the dimensions that width is 300 and overall depth is 500, and we have 5 number of 25 bars. 25. 5 number of this is 5 number of 25 bars, 25 millimeter diameter bars, and there is some effective cover also. I don't know, and we have M15 and we have Fe250. So the materials we have M15 concrete and Fe250. So I would say that we should take some effective cover. It's not provided to you, and for that we have some IS code recommendations. IS code recommendations that on different conditions of weather, environmental conditions, we have different minimum cover of that. From the bottom, how much clear cover is there? There is some clear cover. So we should have some clear cover. That code tells what should be the minimum clear cover corresponding to different what you call as environmental conditions. So if we talk about different conditions, I would say, what is the condition? Exposure condition. What is the exposure condition? So first one is that mild condition. When we say mild, when we say moderate, when we say to square be severe and very severe, and we have extreme. So we can remember that in this way, that this is M2 square very extreme. So that means M2 square very extreme. That means we have 2M. After that we have square. After that we have very extreme. Then finally this V, and finally extreme. MMSVE. MMSVE. Okay. Then for that we have different clear covers. Minimum what you call as minimum cover. For this one we have minimum cover of 20 millimeters. We have this one as 30, 45, 50, 75 millimeters. I mean, this is the minimum value we can take. Minimum value. And if you say what is the minimum grade of concrete we have to use for those different environmental conditions, minimum grade of concrete. So we say you start by M20. After that you increase by 5. So this is the minimum grade of concrete we can have. 30, 35, 40. Okay. Now I would say in this equation we have what was the problem? So we have M15, but IS code IS 456 is saying minimum grade of concrete should be M20. So actually this is the problem that is that was given to you, that was designed in some 90s. So we can still solve it. IS 456 for M15. Okay. So based on this one, I would say there is some clear cover of 20. I can assume some clear cover minimum. Let's take if I take clear cover here in this problem, some value of 25. Let's take some clear cover as 25. Take clear cover as 25 millimeters, and I can get the effective cover also. If I know the bar, I can get the effective cover, that is clear cover plus that half of the diameter of the bar. Can I say that? We say that up to this level this is clear cover, and to the center of the bar we say that is effective cover, and that effective cover is clear cover plus diameter of the bar divided by 2. Okay, so your diameter of the bar is that you have not 25, we have M. This one is not 25, this is 20 millimeters. So I would say your effective cover is clear cover plus 20 millimeters divided by 2. So 35 millimeters. And from that you can say what is the effective depth. We can say then that is d minus effective cover. So total depth was given to you 500. You subtract by 35. Subtract minus that, we say minus 35. Finally, you would get 465 as effective depth. 465. Let's take that value 465, and finally we are going to solve that problem now. 465. Now the data provided to you now. Let's highlight that. We have this width of B. We have this small d, 465. Okay. We have M15. We have grade of steel provided to you. We have area of steel also provided to you. We need to get the moment of resistance. This is the part one. When we know the BD, when we know the cross section, we have to get the value of moment of resistance. That's easy. What is the first step we have? The location of neutral axis. Fy 0.87 Fy AST. AST, what is the value of AST? 5 bars we have of 20 millimeters. 5 times pi by 4 d square divided by 0.36 FCK. 0.36 FCK and B, and that value x equals to 210.8 millimeters. And now we need to get the axial limiting, and that equals to K times D. And for mild steel, that is 0.53, and your depth is effective depth 460. So that equals to finally 246.45. And I would say your limiting condition, that XU is actually lesser than this, XU is lesser than XU limiting. Can we say that? And that means this is under reinforced section. Can we say that section is under reinforced? I would say section is under reinforced. I would say section is under reinforced. Yeah, I would say section is under reinforced. Okay. So then after that, I would get the value of MO, or moment of resistance. So that we can write the equation, moment of resistance. Moment of resistance equals to 0.36 FCK B. The value of B was provided to you as 0.36 FCK B XU. So we have to take XU, actual value, actual neutral axis location, XU, and we have this factor D minus 0.42 XU, and we can get the moment of resistance equals to that's 129 kilonewton meter. 129 kilonewton meter. And we can also solve it by that equation 0.87 Fy AST. We know the AST. We have this AST. We have that D minus 0.42 AST. D minus 0.42 XU. And if you solve it by this equation also, you can get the same value, 129 kilonewton meter. Let's go for the third problem. Let's take the third problem we have. Let's take the third problem we can have. So we have some steel provided to you. I have given to you some steel, and we need to get this steel AST. We need to get the AST. We need to get the AST. How much should be AST? So we don't know how much bars are there, and I need to get the value of steel, area of the steel required. If the dimensions are given to you, that width is equals to 400 millimeters, and we have what you call as you had capital D. Capital D is overall depth is 800 millimeters, and we can assume that effective cover is 50 millimeters. If I say we have M20 and we have Fe415, if I assume that clear cover is somewhat, if the code says minimum clear cover should be 25, that means I can take any value such that if I add that some diameter of the bar, there is generally we have 20 millimeter bar, 25, so that's around 10. So if I say that my clear cover is somewhere 35, 35 plus that 10, that's almost a 45, or finally I can say 50. So generally you should take, you should go that effective cover should be almost equals to 50, or sometimes you can take 40, 50. Okay, no problem. 40, 50 you can take. Let's take it 50, effective cover as 50. So we can take effective cover as 50. If you take effective cover as 50, that means your small effective depth, that is 750 millimeters. So once we know that, also we need to get this AST. We need to get the area of the state required. And if the moments applied on the cross section, we have applied this moment of that's working moment. We have applied working moment of 200 kilonewton meter. So this is working load. So when you talk about limit state of collapse, it talks about ultimate loads. And for that we have load factor combination. And this more working load is occurred because of dead load and live load. And for that we have combination 1.5 dead load plus live load. And accordingly we can have, because of the dead loads, we have moments, and that's your working moment. And when you multiply that factor of 1.5, so that's your that collapse load, collapse moment, or ultimate moment you are applying on the structure. Because we are talking about limit state of collapse, that's limit state of collapse that's related to flexure, limit state of flexure. So for that we have to take what we call as factor moments. We can write that also. Let's remove now. Okay, so that means once this is the data provided to you, let's try to get the actual solution. Let's try to write the solution now. Let's try to write the solution. I would say your factored moment, m factored external, I would write that as MUE. U means ultimate and E means external. That is equals to 200 kilonewton meter into this factor of 1.5. That's 300 kilonewton meter. Now I want that what you call as I want under reinforced section. For that I want to ensure that your limiting moment is greater than M external. I want to ensure that my limiting moment is greater than external bending moment applied, factored external bending moment applied. Okay. Now, can we get the value of limiting moment of resistance? I want to see whether my limiting moment of resistance is greater than mu external. I want to see that because I want under reinforced section. For that, I should get the value of limiting moment of resistance. Can I get that equation? Can I get that value of limiting moment? I think we can get that. I think I can get that also. I would write the equation for moment, limiting moment. Mu limiting equals to 0.36 FCK. There you have FCK 20, FCK B, then XU. Then we have to keep as XU limiting here. This is your XU limiting, and the value of XU limiting equals to K times D. What is the K value we have for this Fe415? Is that 0.48? So we can write 0.48 into D. D is 750. So we can write that here 0.48 into 750. This is the equation. And after that we have that lever arm factor. Of D minus 0.42 XU. So we have to keep as XU limiting. So I would write D minus 0.42 XU limiting. Then we can solve it, and I can get the value of MU limiting comes to be equals to 620.84 kilonewton meter. Now you have to compare that. What's the external moment we have? What is the factored external moment we have? That's 300. So I would say that your limiting moment of resistance of the section, it's even bigger than the external bending moment. So I would say that means your section would be definitely as under reinforced section. If it was equals to this one, I would say the section would be balanced. But your value is greater than this one, so it is under reinforced section. That means the AST you have to solve. We have already talked about that. So AST you have to solve corresponding to, not corresponding to MU limiting, not corresponding to MU limiting. You have to say what is the AST required. That is we can directly correspond it to MU external. So AST limiting is not there. So we have to take area of the steel corresponding to given condition. So that's your area of the steel. So let's write the equation. What should be the area of the steel required? Area of the steel required equals to 0.5 FCK. FCK, what was FCK? 20 megapascals. Yeah, M20. FCK by Fy into BD into BD into BD. B is 400, D is 750, 400, 750, BD. Then we have this bracket 1 minus root of 1 minus root of 1 minus root of then 1 minus 4.6. The bending moment that is external, I would say here MU external, and that was 300 kilonewton meters. Was that 300 kilonewton meters? I think so. Divided by FCK BD square. FCK BD square, BD square. So this is your area of the steel required, and we have to keep that this part. We have to solve it in this way, that 4.6 into 300 into 10 power 6, such that units are in Newton millimeters, Newton and millimeters. Finally, I would say this is in this is 20 megapascals. It is Newton per millimeter. This is your that megapascal also. This is millimeters. This is also millimeters, and this is in Newton millimeters. And we have this Newton per millimeter square. This is millimeters, and this is millimeter square. Finally, you would get a value of AST as millimeter square. Millimeter square. You should get final value as millimeter square. Okay. So that value of AST required is equals to 1209.6 millimeters square. Okay. Let's take that fourth problem. We can take fourth problem. Let's go for the fourth problem. We have this B equals 250, and we have some steel provided, and we need to get that AST. Some AST is there, we don't know. We need to get the value AST for tensile reinforcement, that is the steel area in tension zone. AST for resisting, we are applying that moment of M factored. It's directly saying we are applying factored moment now. M factored equals to 70 kilonewton meter. That means M working is 70 by 1.5. 70 by 1.5. Okay. So this is our factored moment. That means we can write it as MU external 70 kilonewton meters. Okay. Now, so material is M20 and steel is Fe415. So it directly saying that effective depth is 415. That effective depth is 415. Effective depth is 415. It does not give the data of that effective cover. We don't care about effective cover. It's directly saying effective depth is 415. Can you get the equation? Now similarly, we would say what is the value of to design the AST, I would say I should prefer under reinforced section. For that, I have to ensure that limiting moment of resistance is greater than M external bending moment, ultimate factored bending moment because of those external loads. So let's try to write that MU limiting. Let's try to calculate MU limiting. So we have that equation 0.36 FCK, 0.36 FCK 20, FCK is 20, 0.36 FCK B, and axial limiting is 0. Corresponding to Fe415, your value of K equals to 0.48, corresponding to Fe415. So I would write 0.48 into D. So this is axial limiting. This is axial limiting. And we have this lever arm factor of D minus 0.42 XU. D minus 0.42 XU. What is the value of XU? That we have to keep as axial limiting. Axial limiting. So that we can solve. So we would get a value of mu limiting comes to be some value. I have not solved it that way, and you can get some value. So let's try to get the value. Let's try to write that value. 415 minus 4.42.48, and we have this 415. Is it same? Is it d minus 0.42 xu? D minus 0.42 xu, yeah. Is it 415? Then we have this factor of 0.48 into 415, 250 into 20 into 6. This is 11 divided by 10 to the power 6. 118.8, 118.8 kilonewton meter. Mu limiting, 118.8 kilonewton meter. So what is the external factored moment you're applying? That's only 70. So I would say your limiting moment of resistance is even more than 70 kilonewton meter. Okay, that's mu external. So I would say the section is under reinforced section. So the area of the steel is corresponding to the actual factored moment you are applying. So the actual AST would be now equals to, which implies that AST equals to 0.5 FCK by Fy into BD into B into D into that bracket 1 minus that under root of 1 minus 4.6, and the value of M we had to substitute here 70 into 10 power 6 divided by FCK into BD square, B into D square. Then finally close the bracket and get the value of AST. AST equals to 521.8, 521.8 millimeters square, 521.8 millimeters square. So this is one approach. This is one approach we can take. This is one of the approaches we can have. Second approach is that if I want, see, I want under the reinforced section. For that I can solve by this way, or I can solve by this way also, and I can solve by this way also. So I can solve by either of the ways. So I have solved by mu limiting should be greater than mu external. So I have solved by this way. You can solve by xu limiting way also. Let's try to see how. If I write that, if I solve what is the MUE that we know, that was 70 megapascals, 70 kilonewton meter. This was the external bending moment applied. If I from this one I can get the AST required at that value. Can I get that AST required at that particular value? Once I got that value at that location, I got 521.8. Now I can say I can compare now PT versus PT limiting. That's we can compare now. We can now compare AST versus AST limiting. If you are solving by a second approach, this is second approach, AST versus AST limiting. Now I need to get the, once I get the AST corresponding to 70 kilonewton meter external moment, I would say what is the AST limiting we can have? That we can equate from the equation that C equals to T, and from that I would say 0.87 Fy AST limiting equals to 0.36 FCK B. Then we have XU limiting, and you substitute those values, you would get a value of AST limiting, and AST limiting comes out to be equals to AST limiting equals to 993.1 millimeters square. So I would say your AST limiting, AST provided, that is AST required, is lesser than AST limiting. That means the section is under reinforced section. That means that the steel required should be only this part that we have already solved for. So this is second approach. Third approach is that if you want to get in terms of XU, if you want to solve it in terms of XU, I have to ensure that your limiting that what you call as limiting depth of neutral axis, that is K times D, we already solved that 0.48 into that depth of 415. That we have to ensure that your actual XU is lesser than this one. So how can you get the actual XU? For that we need the actual steel required. So once we got that actual steel required corresponding to your external bending moment, so finally I got 521.8. So I can equate that C equals to T. So I can write 0.87 Fy into that 521.8 millimeters square. Then we have 0.36 FCK and B. That's your XU actual. And if you solve that XU, that comes out to be equals to 104.68. And by comparing that with respect to that axial limiting, I would say this value is lesser than this value. So that's also under unfiltered section. So finally, you can take the final value of steel required is equals to 5 to 1.8. 5 to 1.8. Okay. Now let's go for the one more problem. That's problem 5. Let's take the problem 5. Problem 5. Problem 5. Okay. So let's take the section. Let's take the section as we have a few bars provided to you, and we have overall depth. This is overall depth equals to 300, and we have width of 150, and we have effective depth, or we can say effective cover is 50. Effective cover is 50. That means effective depth equals to 250 millimeters. 250 millimeters. And see the difference. See what's provided to you. We have not given to you steel as 250 415 500. No, we are giving to you steel. The steel is having yield stress. Yield stress of the steel is 2100 kg per centimeter square. And the value of G, that's acceleration to the gravity, that we assume that that's 10 meter per second square. Cube, the concrete cube strength equals to 200 kgs per centimeter square. And we need to get moment of resistance. We need to get the moment of resistance of the section. And FCK, and we have 3 number of 16.5 bars. So this steel is 3 number of 16.5 bars. So the area of steel is 3 times pi by 4 16 square. Okay. Now we need to say get the moment of resistance for the section whose dimensions are provided to you. Steel is provided to you. You need to get the moment of resistance. So what should be the procedure? That's easy. Get the location of neutral axis. After then compare it with limiting XU. Then see which of these is suiting for you. Okay. Let's go for that. Let's go for that. I would say first step is that XU. So that equals to 0.87 Fy AST by 0.36 FCK times B. Now, from the data provided to you, your yield stress is now 250. So I would say this is 210. 210, that's 2100 kgs per centimeter square. And that I can directly say this would be 210 megapascals. If the value of G is 10, that means the value of that Fy would be 210 megapascals after solving that. After solving this, I would say your value of Fy would be 210 megapascals. You can solve it. Let's try to solve it. Mass into acceleration. So I would say 2100 into that kg. Let's try that 10 meters per second square into this kg divided by centimeter square. That means we can write it in this way, or we can write it in terms of millimeter square. I can say this is 10 to the power 2 mm square. So finally, you would get some value. This is 100. This is 10. Then finally, you are left with 10. So 10 and this one of the 10 goes. So finally, you got 210 kg meter per second. Kg meter per millimeter square. That's Newton per millimeter square. So finally, this is your equation for yield stress. So once you got the yield, and similarly for the cube strength, that's 200 kgs per centimeter square. 200 kgs per centimeter square. You can say this is 100 millimeter square, and from the top we have kgs and we have 10 meter per second square. And finally, you would get a value of 20 megapascals. You would get some 20 megapascals here. You would get 20 megapascals. 20 megapascals. And we can substitute those values. So I would say 0.87 Fy AST. AST is 3 bars of diameter 16 divided by 0.36 FCK and B. What is the B? We have 150. So that's your location of neutral axis. XU is equals to 102.04 millimeters Now we need to get the limiting neutral axis location, axial limiting, that is k times d. What is the value of k? 0.53, 0.48, 0.46. Can you tell me which of these values we should use? Which of the values we should use for that steel of yield stress 210 megapascals? What do you think? What do you think? So we had one general equation once we derived that equation of k, we got that equation of that axial limiting was equals to some factor of k into d. The value of k was actually some equation we have 700 by 1100 plus 0.87 Fy. This is the equation we had derived during that what you call as a derivation of that uh, limiting condition for neutral axis. So this was your value of k. Now we have to substitute the value of Fy as 210 megapascals for this condition. 210 megapascals. And once you solve it, you would get a value of k comes to be equals to 0.546. 0.546. So axial limiting equals to 0.546 into value of d equals to, what was the value of d we have? 250. And this value is equals to 136.431. Now compare that XU and XU limiting. Compare that. I would say XU is lesser than XU limiting. So I would say XU is lesser than XU limiting. So I can get the moment of resistance easily corresponding to this value of XU. So that is 0.36 FCK, and B, what was the value of B? That is 150 millimeters, and XU as 102.04, and then the lever arm of D minus 0.42 XU, D minus 0.42 XU. So value of MO of the section corresponding to XU is equals to 22.83 kilonewton meter. Okay, let's take problem 6. Let's take problem number 6. Problem number 6. Okay. So we have some steel provided to you. There's some AST. AST is provided to you. Four number of 25 bars. And the overall depth is D 550. Overall D 550. Your width of the cross section is 230. And there is clear cover. Clear cover is given to you as 30 millimeters. Clear cover is 30 millimeters. And we have M20 Fe415. We need to get the moment of resistance of the section. So from this, I would say, what is the value of D we can have? Can you tell me the value of D? I would say that value of D is 550 minus effective cover. What is the effective cover we can have? Effective cover would be clear cover minus diameter of bar divided by 2. Diameter of bar divided by 2. So that is 510. 30 minus 10, that's 40. 510 millimeters. So let's try that. First step, that XU equals to 0.87 Fy AST, 4 number of parts of area pi by 4 20 square, and divided by 0.36 FCK times B. So XU comes to be equals to 273.97 millimeters. Now second step is that get the value of XU limiting. What is the value of XU limiting? XU limiting is 0.48 corresponding to Fe415, and the depth was that effective depth of 510. So that is equals to 244.8 millimeters. Now we can see that your XU is actual greater than limiting condition. So XU is greater than XU limiting. What is the section that has developed? That means the section is over-reinforced section. So what do we need to do now? What we need to do? We have to calculate the moment of resistance of the section. So we say moment of resistance corresponding to the section that is having dimensions BD and some steel is provided to you. So once those dimensions are fixed, you can't revise the section. You can't revise the section because the data is provided to you. Steel is provided to you. B and D is provided to you. You don't have to revise the section. You don't have to change the dimensions of the section and steel. We are saying corresponding to this condition, what is the moment of resistance of the section? I would say I don't want that moment of resistance at the value of actual XU for the over-reinforced section. If I calculate it in this case, if I calculated moment of resistance of the section at the rate of actual XU, that would be greater than MOR at the rate of XU limiting. So even though the moment of resistance on the actual case, if I substitute the value of X as 273.97, I would get moment of resistance more from the section. But I should not prefer that. Why? Why I should not prefer that? Because once your strain in concrete has reached 0.0035, the strain in steel is lesser than the limiting condition of 0.02 plus 0.87 Fy by Es. That means your steel is not properly utilized when the concrete has cracked from the top side. So concrete has cracked, but your steel is not utilized. So I should not prefer that moment of resistance. I would say our moment of resistance should be corresponding to limiting condition. I should apply the loads such that your moments are external moments are lesser than limiting moment of resistance. That would ensure my section as under-reinforced section. So this is the first step, that once I check it, that I should ensure my moments. I am going to, why I am solving for only MU limiting. The thing is that because MOR corresponding to what you call as XU actual, because of that section is under over-reinforced section. In this case, it is more, but it would ensure that your steel is not getting yielded. Steel is not going to yield. That means it's not a better way to have. So I'm solving the MU limiting in this way, that if the load I'm applying the load such that your external bending moments are lesser than, I have to ensure that my external bending moments are lesser than MU limiting, and this condition will ensure that section finally becomes under-reinforced section. So this is the actual way we have. So finally we say corresponding to this condition, now I am solving not MOR at the rate of XU actual. No, I am not going for that. I am going to solve this problem now. Finally, MOR at the rate of limiting condition. So I need to solve MU limiting. So for that, I would say the equation is 0.36 FCK into B and XU limiting. XU limiting as 244.8, and the value of D minus 0.42 XU. The value of D, what was the value of D? 510 minus 0.42 XU limiting. So this is our equation, and finally limiting moment of resistance is equals to 165.06 kilonewton meter. So this is the limiting condition of moment of resistance. Now the second part of the problem is that now once we got the limiting moment of resistance, we need second part of the problem, part B of the problem. It's saying that get the intensity of imposed live load. Intensity of imposed live load excluding self weight self weight, excluding self weight, and yeah, the beam is simply supported for 5 meter span. Beam is simply supported for 5 meter span. Beam is 5 meter span and simply supported. Simply support beam. Simply support beam. That means the beam is in this fashion. Some cross section is there. The cross section is provided to you, and the length is effective length is between the supports effective length of 5 meter, and there's some load UDL acting here. One is that it is because of one is the self weight, and one is that live load. So we need to get the live load value. We have to exclude the self weight from that. So I would say your moments, I would say equating that your external moments because of the loads, they should be lesser than limiting moment of resistance. That should be lesser than limiting moment of resistance. If it's all by that approach, I would solve by that approach, I would say.
Okay. Let's try to get that. Can you tell me what's the external bending moment we can take? Let's say the intensity of the live load, external live load, that is WL, and because of the dead load we have WD. I would say for the simply support beam we have maximum bending moment of WL square by 8, and that's corresponding to service load. That's corresponding to service load, and I want factored load, ultimate load. So MU ultimate would be 1.5 times ME service load. And we need to get the dead load. What is the dead load? Can you tell me what is the dead load? We have to remove that part, dead load. So let's write that we have general value of W. First, let's write that we have finally some value of W. This is some value of W. So finally, I would say WL square by 8 into 1.5. So I would equate that. I would say external moments, that's W into 1.5 into L square by 8. L square by 8. That should be lesser than limiting moment of resistance. I solved that limiting moment of resistance 165.06. So 165.06 kilonewton meter. So my loads should be such that they would cause the bending moment external lesser than limiting moment of resistance. So we have those dimensions. Length is 5 meter, length of the span. So intensity W into 1.5 into 5 square meter square divided by 8. So you would finally get that intensity. You would get that loading intensity. Loading intensity should be less than or equal to, I would say less than or equal to, what do we have? 35.21 kilonewton per meter. And this is the, we would say this is all. We would write it as W all because of live load and self weight. So finally, I would say what should be the live load we can take? The live load we can take, that should be lesser than total load, total intensity 35.21 minus dead load intensity, dead load WD, dead load intensity. And we need to solve WD. What is the WD we have? What is the self weight? Gamma into BD, kilonewton per meter. So actually we have to take capital D, capital D. This is the section, B into D. So I would say gamma is, we can take either 24 or 25. Sometimes we take 24, sometimes we take 25. So let's take 25. 25 kilonewton per meter cube. And the value of B, what is the value of B we have? We have the width of 230, and overall depth of the section is 550. Overall depth is 550 and width is 230. 230, 550. 230, 550 millimeters square. And you can solve WD equals to 3.16 kilonewton per meter. So we can say, what should be the live load we have to apply? What should be the live load we have to apply? So the live load we have to apply is equals to 35.21 minus 3.16. So W live load should be less than 3.35. 32.05 kilonewton per meter. Or finally, I would say this should be less than or equal to this value. Okay, this should be the safe load, safe live load that we can have, safe live load. Why we are saying this is safe? We have already accounted that factor. Already we are accounted that factor outside. So this is the safe value we have, safe value. And overall, this is ultimate value. This is mu ultimate external. Okay, do you got this problem now? I think this was the best one. Out of these, this one was your beautiful problem. This was the beautiful problem we can have. Let's take problem 7. Let's take problem 7. We had to prove that limiting moment of resistance that we represent here as mu using stress block parameters. The parameters of the stress block is that your lever arm equals to z, d equals to d minus 0.42 xu, and one more data is that your pt, percentage tensile reinforcement, is pt, that is ast by bd into 100. Okay, and we had to prove that mu equals to 0.87 fy pt by 100. Then we have 1 minus 1.015 fy by fck. We have pt by 100, and we have bd square. This is what we have to derive. We have to derive this one. So I know one of the equations of moment of resistance corresponding to T into Z, tension force and Z. Do you know that equation? I can see that there's some clear relation there somewhere. If I know from the stress equation, we have stress block equation, I would say moment of resistance mu equals to 0.87 fy ast and d minus 0.42 xu. I know this equation. This is the equation I know based from the stress block parameters. Okay. Okay. And you would see that what are the same parameters we have from this equation. I would say 0.87 is here, 0.87 is here, fy is here, fy is here, and this is any other thing we have. So I have to convert this part I have to convert in terms of this one. So I have to convert it in terms of this one. So let's try to have that. I would say from the data given to you, ast can be converted to pt as ast would be equals to pt bd by 100. ast equals to pt bd by 100. Let's try that. ast equals to pt bd by 100. So I would say, so finally I would say 0.87 fy ast. I have to remove that ast by pt bd by 100. pt bd by 100. So pt by 100 into bd. So I got this part. Then we are left with d minus 0.42 xu. Now this part is over. This part is over. This part is over. And from this one we have bd square. So I would say bd is over. bd is over, and we have one more d also. So we have to convert now this part into that d in terms of this one. That means this d should be kept outside. This d should be kept outside from this equation. So we have to use that equation of xu such that I can replace xu in terms of this one that we have. So if I know the equation of c equals to t, from that I can have the equation xu equals to 0.87 fy ast by 0.36 fck b, and ast is not there. We have the ast in terms of pt here in the equation. So I have to convert the ast again. So let's try to convert that again. 0.87 fy by 0.36 FCKB. Then we have AST. AST is in this value. We have to write PT by 100, and we have this factor of B into D. And can you get some value here? Some sort of value we can have from here. And if you solve this one, and any other thing we have, Fy by FCK. Fy by FCK is there. PT by 100 is there in the equation. This one is there. This one is there. So I can substitute that value here. Let's go for the equation. Let's go for the equation. I would say I got the equation of 0.87 Fy, PT by 100. Then we have BD. Then we have D minus 0.42 XU. 0.87 Fy by 0.36 FCKB. Then we have PT by 100. Then we have this factor of B into D. B into D. And we can keep the D outside such that it becomes finally BD square. So if you remove that D, if you kept that D outside, I would get finally BD square. So this part is over. Now I would say if you solve this 0.42 into 0.87 divided by 0.36, and you would get a value of 1.015. And finally you are left with Fy by FCK and PT by 100 in the bracket. So then we have this part also here. 87 Fy, PT by 100. Then finally we can say BD square. So this was we had to derive. Okay. Let's take problem 8. Let's take problem number 8. Problem number 8 that we have. Problem number 8. We have this RCC beam cross section. This is 300, this is 600, and we have 4 number of 25 bars. And effective cover is what you call as 50, and that means something. So we would say keep that outside here. I would say we need to get ultimate moment capacity. Ultimate moment capacity. So that's moment of resistance. And after that we say what should be the safe working loads. Well, we also note that safe working loads. Safe or working loads. When we talk about safe, that means it's talking about safe or working loads. And that too as a live load. Okay. We already know load factor is 1.5, and Fy is, so we have the data for the material. Fy is 2500 kgs per centimeter square, and we can say that means 250 megapascals. Fy is 250 megapascals. FCK, that means M20. FCK is M20. Okay. Dead load, we can have. Okay. Effective span is 6 meters. This is the span of that beam, simply supported beam, 6 meters. And we have some UDL, dead load plus live load, that we need to calculate also. So let's take some break here.